So let's discuss a problem from SFD and BMD. This is an interesting problem because it will test your understanding of SFD and BMD. So a loading diagram is given and the loading is a triangular loading, triangular uh, distributed loading, and the likely possible candidate for the shear force is asked. Okay, so a couple of things we need to understand before going to the shear force. To answer this question, the shear force diagram, the shear force at any point, okay, is basically how do you get the shear force at any section, okay, so will be basically the area, okay, so area of the curve, okay, this you can get from the area of the curve, area of the loading, area of the loading diagram. Okay, if it is a distributed loading, otherwise it will just summation. So area of the loading diagram in distributed case. Okay, distributed case. And also the second fact which is again will be used here is the slope of the shear force diagram at any point, the shear force at any point, okay, is equal to the load intensity W, is equal to the load intensity W. And this is again, these are all small derivations. So df by dx, I should say, is equal to W. I mean, there, depending on the sign convention, you may find out in some books a plus or minus here, but the basic idea is that the magnitude of the slope is equal to the shear, the loading intensity. Okay, so this fact we can use it here, and also the 1 and 2 combinedly we will use and try to remove the odd man out and try to figure out. Now if you start here, what is W here? The W is 0 because you don't have intensity here, okay, and slope of the shear force diagram is equal to the value of, that's what the point number 2 says, the slope is equal to the value of load intensity. So the slope has to be 0 at the start. So going by there, I think the possible candidate, I mean, these are not correct because here if you see you have a finite slope here. So B is wrong and D is also wrong because you have a finite slope here. So point number 1 is that W is 0 and slope is 0. Now if you come here, as you travel from right to left, the value of the shear force will increase because if you take any section, the right side area of the loading diagram will give you the value of the shear force, and as you come towards left from right, the area of W is increasing. Okay, so A and C both represent the same thing. They represent the same thing. Okay, the value of the shear force is increasing, but there is a difference in the slope. Okay, here the slope is continuously changing from 0 to finite. Now coming to the fact here, if you look at the value of the shear force, the value of the shear force is finite, and that is actually area of the curve, which is half base into height. It's a triangle loading, so half W into L. So WL by 2 is shown in both A and C, so that is correct, the value is correct. But let's check the slope. Slope here is also equal to W. It's always the load intensity. Load intensity is 0 here. So slope has to be 0 there, my dear. And this represents a finite slope. Take a thing, it represents a finite slope. Positive and negative, just leave it because it again depends on the sign. So here it's a positive slope. But here, if you look, if you take a tangent, how do you find out a slope? It's a tangent. So slope here is 0. So both these facts have to be correct. Slope at the ends have to be 0 because the load intensity is 0 there. And so from 0, the slope starts from 0, it peaks somewhere in the between where the load intensity is maximum, W at the middle, so it peaks there. Therefore, if you draw a tangent there, you will know that the slope is maximum, and then it again goes to 0. So C is the best choice, and C is the choice. In fact, A fails because slope even at end B is satisfied, but at end A is not satisfied. So these two things remember, and most of the time the slope fact will always help you. Okay, thank you.